Yeah.
Carol is the country lead for Syria, and meet Dr. Reza and Thomas, our distinguished speakers for today. And
Nice to meet you.
yeah. And Tahia Islam, the woman you've been talking to so far, she is the country lead for Bangladesh, her will. So that was a brief informal introduction before we started. And one other thing I wanted to mention, hey Tahia, who is going to be answering the questions from the intern side? I thought Ramisha would have been really good, but it's okay if you assigned it to somebody else.
Rina, Suraya, and Farhi.
In leadership and data science and AI. So let's start about more logistics and more operation with Tahia. Please, Tahia, could you share more information about how to start?
Thank you so much, Aya. I hope everyone can see me, hear me. Welcome everyone to our workshop 2, which is on AI basics and advanced text processing with Python. I would like to introduce 2 of our very wonderful instructors. I am apologizing in advance if I not pronounce your names correctly. One is Dr. Reza Zannat and another one is Thomas Bruys. Dr. Reza is a research engineer in Milton Stewart School of Industrial and System Engineering at Georgia Tech, and Thomas is a PhD student in electrical and computer engineering at Georgia Tech. So I will leave all of you in the hands of these beautiful instructors, and I will not take much time, but what I would like to say is that any kind of information that you require regarding the Google Classroom, regarding the recording of the previous session or the current session that is going to happen, you will get all the information in email, and you will also get all of those information in the chat box as well. So for the next 2 hours, just enjoy and learn as much as you can, because that is the only reason that all of us are here. So without further ado, I'm handing over the floor to Dr. Reza. Dr. Reza, please let me know if you can share your screen perfectly and if you can handle all the technical things. If you need any support, just let me know.
Sure. Thank you, Taya. Hi, everybody. First, I would like to thank Herville team for making this happen and having us here. We're also so excited about this workshop. Can you all see my screen now? If
yes.
Somebody can
yes.
confirm. Okay, great. Today we are going to talk about AI basics and advanced text processing. So I will first go over some outline of, so I skip this slide. Thank you for the intro. I will first go over the outline of the presentation and what we are going to do today. And at any point, if you feel confused or if you have questions, please use the chat to send your questions there. I will also try to keep it more high level and some parts skip the math and give you more intuition. There are some math, but the goal today is to give you more intuition about what is happening and give you more background about AI and how to use AI for text processing. So we will first start by overview of machine learning, and then we will move to supervised learning and Bayes decision rule. Then we'll talk about classification and regression problems. After that, we will pause and Thomas will walk you through some notebooks that you can implement, that there are some implementation of some basic classification models using some interesting examples. And then after that, we will talk about neural networks and we'll look at TensorFlow Playground so that you see how training of neural networks works and how changing parameters will affect the output. And then we will talk about natural language processing, text pre-processing, word representation, word2vec, and then we will move to 2 other notebooks that you can again use to learn how to process the text, and we'll have some text classification and word representation examples as well. So first, let's talk about machine learning. see if I can pin this so that it doesn't come down. Okay, never mind. So what is machine learning? It's a process of developing algorithms and models that can learn to make decisions by looking at the data without being explicitly programmed. And this can be as simple as differentiating between these two figures that we have here. We have a circle and a square, different colors. Or it can be something like detecting the faces in that image and then recognizing the people. It can be more complicated for predicting and forecasting time series, like in power system. This example that you see, it's a wind power generation in the US in one of the wind farms that you want to predict the outcome based on the historical data. Or it can be even more complicated for predicting behaviors and developing self-driving cars, which you have to combine many different models and have data from multiple modalities and combine them to make the decision and make sure that you are respecting the safety and you are developing a model that can be used in real world. So there are different types of machine learning, and I'm going to give you an overview of a few of those. The first one, which we will be focusing more today, is the supervised learning. So you can consider this as learning from some labeled data to predict the outcomes on some new data that you have not seen before. So in this setting, we have a data set that has pair of input and outputs. So these X data points, X1 to Xn, are our input features. Like it can be the height of people if you're making prediction on, let's say, somebody is giving a disease or not. It can be some individual demographical features about those people. And then the Y is the outcome, which can be multidimensional or it can be one-dimensional. It can be continuous or it can be discrete, which we will discuss that further in the lecture as well. So you can consider this problem as a function approximation. So you want to learn some mapping from your input space to this output space, given some data. And one example for it is to learn to recognize digits from handwritten digits and see whether it's 0, it's 1, based on some input images that you have. So you train your model on that, and then you want to test it using some future data that you have not seen before. And you want to make sure that your model is generalizing well on those instances. The other type is unsupervised learning. In this scenario, we don't have the labels. We just have the input data. And the goal is to learn a mapping that you can come up with a compact representation or description that can give you some intuition and unlock some patterns that exist in the data. One example of this is in network analysis, like in social media, or it can be network of people purchasing products on Amazon or other retail websites. And your goal is to form this network and then recognize communities that they have similar behaviors by clustering the nodes, which here can be people, and then the edges can be the relation between people in a social media. So you want to cluster those based on their behaviors, and then hopefully make some decisions afterwards based on that. The other type of machine learning models is reinforcement learning. So in this setting, it's a bit different than the previous ones. You do not have labeled data, but what you have is some reward or feedback that you can get from your environment. And your goal is to make optimal decisions through some trial and errors and interacting with an environment. And finally, you want to maximize your reward. So in this example, we have an agent which is interacting with the environment. And then each action that this agent takes that agent to a new state, and then the agent will receive a reward, and based on that, it will revise the policy and then continue so that it can optimize the policy. And this can be, for example, teaching some robots to walk, and then initially the robot starts to walk. It cannot walk too far, and then over time, the goal is to make sure that it can go as far as possible. And by giving positive rewards when the robot is doing well, then the hope is to teach it to walk as much as it can. And it has many different use cases in medical domain, as well as the other applications that we discussed, supervised and unsupervised learning, where you have control problems. So let's talk about supervised learning and classification problems now. So the classification problem can be considered as a mapping from one input space to a categorical or discrete space. So you want to predict some classes given the data. And the first thing that we need to discuss here is Bayes' decision rule. So if we have the probability, this P of Y, consider this Y as being your class, either class 0 or 1, whether somebody has a disease or they don't have a disease. And this X is your input feature. So sometimes having access to this probability is difficult. So using this Bayes rule, we can translate this conditional probability to what we have on the left and write it as P of X given Y multiplied by P of Y, where we call this P of X given Y as the likelihood of observing X given class Y. This P of Y is our prior, and this one you can consider it as just a normalization factor. Now that we have this, the Bayes decision rule is telling us to maximize the probability of select a class that maximizes this probability. And that results in getting the least probability of the error. So in a binary classification setting, if we have two classes, Y can be -1 and 1, the Bayes rule is telling us to pick class -1 if the probability of class -1, given that observation, that input data, is more than probability of 1 given X, and otherwise select 1. Now, given the Bayes rule that we discussed in the previous slide, we can translate this to the thing that we see on the right. And then these two will cancel out, and then at the end, we can translate the Bayes rule, Bayes decision rule, from making decision based on P of Y given X to the making decision based on the likelihood and the prior. And this prior, again, is some kind of belief that you have about that specific class, some prior knowledge that you can have. And then this one is something that we can learn. And then we will discuss how to learn these decision boundaries and how to make the decision. Okay. Now let's assume that somebody gave us these probability distribution functions. This P of X given Y is this Gaussian distribution on the left. And then P of X given Y equal +1 is the green one on the right. And we assume that the P of Y equal 1 and -1 is just 1/2. So the prior for both classes is the same. So given that, if I select my decision boundary right at the point that these two probability distributions are intersecting, I can say that anything that is on the left is my class negative, and anything that is on the right is my class positive. Now that we do that, and remember that we know the correct probabilities, but something that happens here is that we cannot classify these two classes with 100% accuracy. So there are some points that we definitely make mistake, even in the ideal case. So those are the areas under this curve, because we said everything on the left is class -1. So we are going to miss some data from class +1, and we are going to miss some from class -1, which we classified as 1. And those are going to be our false positive and false negative errors. Now we have to see how we are going to measure how good or bad the classifier is doing. So those are going to be our metrics. The first metric that we usually use for understanding how well a classifier is performing is accuracy. So it's technically counting the number of times that you are making correct decisions and dividing by the total number of data points that you made decision on. The second one is precision, where you want to divide the true positive, this one, over the true positive plus false positive. So this is technically telling you that from those that classified as positive, what portion are actually positive. And then the other metric is recall, which is true positive divided by true positive plus false negative. And this one is telling us from all positive instances, what percentage are classified correctly. And then there is another metric called F1 score, which is technically the the harmonic mean of precision or recall. So each one of these metrics are providing us some overview of how well or bad the model is performing, and each one of them can have their own limitations, which in the notebooks we can also see as we are going through them. Now, so far we consider that somebody gave us that probability distribution, but that almost never is going to happen. We don't have that luxury. So let's see what we can do. So we have to learn from the data, either that distribution function or the decision boundary, that dashed red line that I showed you before, directly. So the solution is to use the training data and learn the decision boundary, which we call them discriminative models. There are some other classes of models that they try to learn the distribution directly. We are not going to focus on those for now. So the goal is to learn the decision boundary. How we are going to do that is, again, use the data and minimize some loss function. The loss function is actually penalizing us for every time that we make a mistake. So we are learning this f function, f hat, the mapping from input space to the output space, and we compare whatever we do, the decisions that we make on that training data, to the actuals, and then based on that, we try to minimize the average cost or the expected cost. So let's first focus on this black line, this one that is like a step function. So the x-axis is comparing y and y hat. So it's multiplying these two. If y and y hat both are from the same class, again, in the binary classification task, one of them could be 1, one of them can be -1. So if we say y and y hat are 1, so we lie on the right side. And if we say both are -1, again, it's going to be positive. So again, we are here. But if we make a mistake on one of them, then we will be on the left side. So we penalize by 1. So this loss technically is telling you that every time that you make a mistake, add 1 more to the loss function. And we can show in theory that this can result in the Bayes decision rule if you have enough data, if you have a lot of data. But the challenge with this loss function is that usually when we want to minimize a function, we work with gradients. We have to take derivative of this function with respect to the input. But this function is not derivative here, and also it doesn't have meaningful derivative here and here. So we approximate it with some other loss functions, which again, we can show that they are going to give us the Bayes decision rule, like log loss or hinge loss, as it's shown here, and then use those to minimize the expected loss over the training data. So one approach to minimize this loss is logistic regression classifier. So considering our input feature vector as the combination of x1 to xd, the logistic regression classifier is modeling the conditional probability that we discussed as something that I show here, where z is just a linear operation on the input feature plus some bias. And then we make the decision based on the following policy. So if the probability is more than 0.5, we say it's class 1. Otherwise, we say it's class 0. So I want to pause here so that we go to the notebooks and go over some examples for the classification for one synthetic data and one other data set that Thomas is going to talk about. So I'm going to stop sharing. And I will check the chat for the questions as well while Thomas starting to share the note.
Yes, so hello everyone. So I'm Thomas and we're going to go through the different notebooks that will give you an overview of what is discussed with Reza. Can someone confirm to me that you can see my screen?
Yes.
Okay, great. So here the idea, as Reza mentioned, we have different problems in machine learning, such as classification and regression. So we're going to focus on a very simple problem at first, which is trying to do like linear separation for binary classification. So binary classification is very important in machine learning because it can help you classify between 2 different classes, 2 different tasks. So the objective is to categorize the data points that you have in the 2 different distinct classes. So one very widely used method for that, and one of the first one, is logistic regression that was introduced just previously by Reza. So the idea is, in this notebook, we're going to use a very simple 2D data set and trying to learn how to separate this data. So I think you should have access to these notebooks through Google Classroom. There are like Workshop 2 AI Basics and Advanced Text. So if you want to open it during the meantime, following the same procedure as Rabab said in the first workshop, you can. Otherwise, you can just follow. I've already run them because some of them can take few minutes to run. So you can play with it later, or you can do it at the same time as me. It's as you want. So, I'm not able to access let me just move this. Yes. Okay, we are back. So what's great about machine learning and Python in general is that you have all different number of packages that can help you in the implementation. So one of the most basic one you see here, I import the necessary libraries for the notebooks. It's not very important to know about all of them, but most of them are open source. So it means that some of the people have built the code and you don't need to re-implement everything from the equations. So you can abstract some of it and use direct packages. So for instance, one of the very famous one is sklearn that you can see it. It's called also scikit-learn, and it's an open source library that is doing like tons of great things about machine learning and helping you to implement different models. You can see I'm importing like different metrics, which are the metrics that were introduced by Reza. And it's helping you also to understand the performance of your model and what's happening. So let's go to our data. So I've generated synthetic data. So you see there are like I introduce here the means, the covariance, the number of samples for each classes, and then I generate normal distributions. So and then we can visualize it. This is also one of the great things about notebooks like this is we can see the data. So here you can see that I have two classes. I have only two features. It's a very simple example. So the x-axis is feature 1, the y-axis is feature 2. So what's great about all of this is that you can visualize the two classes. So red for class 0 and blue for class 1. You can see that there is some overlap between the two. And our goal will be to draw like a linear separations between the two to have the best results and to learn it from the data. So as Reza mentioned, we want to learn from our training set. And why are we talking about training and testing set? It's because in practice, you have access only to some of the data. So if it's temporal, maybe you have access to the data until now, so until October 2024, but you don't have access to the data of December 2024. So the idea is that we split our data set between a training set that is used for the model to understand about the data, to learn from it, to understand the patterns. And then we have a testing set. So you can see it's xtrain, xtest. And the testing set is going to be used to evaluate the model and understand how good it is performing in practice. So now that I've defined my training testing set, I can again visualize them. So you can see here, the stars correspond to the testing set and the rest is the training set. So the circles are going to be given to the model to approximate the best linear boundary. And then we're going to see how it works and what are the performance on the testing set. So we have this data, and then here for this simple example, we're going to use logistic regression. So I'm not going to go over the equation again because it's been introduced by Reza. And we're going to use also a loss function, which is called cross-entropy loss. You don't have to know the details of it, but it's one of the most common functions that is used for binary classification, and it has been expanded to multi-class classifications too. So then you'll see that the syntax is pretty simple. You can rerun it at home too. So I define the number of iterations of my model. Then I just call logistic regression, which will be my model for this problem. So I set the max number of iterations to 10 because it's a pretty simple problem. and then we just have to fit. So fit is going to give the model the training data. So it's giving the features and it's giving the labels here. So once the model knows about this, it will try to generalize the linear border between the two classes. So this is once we fit, it's all good. So then we can extract the linear boundary from it, and you see that I have my linear boundary in blue, which is very good because intuitively we can see that it helps us to split the data in a pretty nice way, and we're happy about it. And now we're able to discriminate between class 0 and class 1 without using too much information. But I told you that what we're interesting about from the metrics perspective is the testing set. So you can see that on the right, it should be the blue, and on the left, it should be the red. But in practice, you can see that some of the blue stars are on the left and some of the red stars are on the right, which means that we are doing some misclassification due to the design of our model. So we can then introduce different metrics. So we have the accuracy, which is 88%. So I guess in most of the practice, we would be happy with an accuracy like this. Then we have the precision, recall, and F1 scores. So this has been introduced in the slides by Reza, and if you don't remember it, you'll have access to the slide and you'll be able to check this metrics again. Then what I wanted to introduce, it's a very common way to evaluate the models and to visualize the results, which is the confusion matrix.
Thomas, sorry for interrupting you. The question that we hear a lot is about the data set. If you can just explain it again, that how this data is generated. Thank you.
Sure. So for this data set, so let me go up. It's just so I have two normal distributions and I sample points from them. So you can see it here. So I have my normal distribution and then I'm taking some points. So I'm basically manually drawing circles and then taking points in that circles. You could see it that way. And it's synthetic, so it's not representing anything. It's just feature 1, feature 2 according to 2 dimensions. And it's just like a synthetic data. So I've used the means. So you see that, for instance, for class 0, the mean is -2, -2. So the middle point should be somewhere here. And you see that it's in fact also almost the center of the points from class 0. And it's the same for class 2. So I've just synthetically created this data. So let me know if there is any other question in the chat that are confused about the data.
I think we are good. Thank you, Thomas.
Okay. So next, so yeah, as I told you, so we've been able to draw that linear boundary. And the next idea is how can we visualize the results and try to get some intuition on how the model is doing very quickly. So in classification, we use a lot the confusion matrix. So you can see it. So here the y-axis is what we predicted, and no, the x-axis, and the y-axis is what are the actual values. So let me go into more details. So for instance, the 28 here, what does it mean? It means that so there are 28 samples that were predicted to be class 0 and that are actually class 0. So, and here, the 3, it means that there are only 3 samples that were predicted to be class 1, but are in fact class 0. So we made 3 misclassifications here. And then the same, so these 4 here, it means that there are 4 samples that were predicted to be class 0, but they are in fact class 1. So basically, the idea is that we would like to have most of the values on the diagonal, and this is the case here, and you can see it with the colors. So in practical settings, we would be happy with that model. But as I told you, it's a very simple model. It's a very simple data set, and it has some limitation. The first one is that the way we are designing the boundary, it's only linear. So it contains a lot of biases based on the data. So here it works well, but you'll see that in practice, it's not that good. So if there is no specific question in the chat about that problem, we can go to the second notebook that will give you more intuition about and more ideas about how it works on real data sets.
Yeah, we are good. I'm monitoring. Yeah, thank you.
Okay, great. So the second data set, again, it's pretty simple, but you'll see that here we have some explainable features. We understand more about the data and about what's happening in the details. So the previous example was more about binary classification. Now, what happens if we have a bigger number of classes, let's say 3, let's say 4, it can be whatever we want. And so I think Rabab in the previous workshop talked, or at least showed pictures about this data set. So it's a very common data set, which is called iris data set. So basically you have some features about the flowers and you want to try to predict what is the type of that flower. So what is the exact species of that flowers, the exact type of iris. So you'll see. So again, I installed some packages because, as I told you, it's very easy to use packages and to learn about machine learning right now because lots of the things have been developed and are user-friendly, I would say. So you can see here that I can directly load my data set. Then I have a set of features, which is X, and a set of labels, which is Y. Then I put them in a table and I show you some samples. So here you can see, so these are like 10 rows of the actual data set. So you can see that one of the features is the sepal length in centimeters. Then you have the sepal width in centimeters. You have the petal length in centimeters and the petal width in centimeters. So, and then we want to predict what is the exact species of iris. And here they are abstracted in 0, 1, 2. So there are only 3 classes. So this is about the data. And now I'm going to introduce to you something new. So previously I told you, okay, so we want to, okay, we want to, sorry about that. So we want to introduce a testing set because this is the test to which, the set to which we don't have access to the labels. But you can see, I think that if you use the testing set to evaluate your model, there will be issues because you cannot iterate again and again. Because if I want to use my data on some of the data in the future, then I won't have access to the labels. And also, I want to have a model that can generalize well. So in fact, what is going to happen is that in my training set, so the set of data where I have both the features and the labels, I'm going to split it further into a training and a validation set. And basically this validation set, we're going to only train on the training set and then evaluate on the validation set. And then based on the results on the validation set, we will maybe change the parameters of the model because these models can have tons of parameters that need to be adjusted perfectly to have the best performance possible in reality. So yes, so this is what happens. So we define that validation set, and it's helping us to determine what are the exact parameters that need to be used for the model. And then, so this step is called like hyperparameter tuning because it will help you to tune and to decide on the best parameters that can be used for your problem. Then there is some pre-processing sometimes that needs to be done because you can see, so sometimes you have to scale the features. So you have numerical features that are numbers. And to some extent, sometimes the model needs to have something that's scaled because it will do some matrix multiplication, it will learn. And if the features are very big, there can be some issues with this. And yeah, and you see there was an error before, but you see that my training set consists in 90 samples, and then I have a validation set of 30 samples, and then a testing set of 30 samples. And so how am I going to do that tuning of the parameters? So here I'm going to use a decision tree as a model. So I'm just going to give you a very quick overview about decision trees, but it's not the main focus of that presentation. So decision tree, it's one of the most common model that is used for both classification and regression, and we'll use it later also for regression. And the idea is we can have a tree, and at each node, we will decide if we go true or false. And based on this, we will try to learn the problem, learn the classes, and also learn the outputs of the target that we want to estimate. So I told you we have different parameters in these models, and we want to select which one are the best and which one will lead to the best performance. So here what we do is we define a grid. So for instance, one of the parameters that are used in decision trees are max depth, the mean sample splits, mean sample leaves, criterion. I'm not going into too much detail, but the idea is that it can take multiple values. So what you can do is to try these different values, and then it will create a grid. So it will try to learn which one are the best based on the results on the validation set. So this is what happens here. So I define the possible values that I want to test for my model. Then I define the grid search. So this is the part of the code that will try to select which parameters are the best and needs to be used on the testing set for the final evaluation. And so once it's done, I filtered, like, I've tried 540 candidates, 540 fits. And now that I'm confident that I selected the best parameters, I can print them. And you see here, so the criterion is Gini, the max depth is 2, and the mean sample leaf. So I've decided on all the parameters that I decided here. And then we proceed to the final evaluation of the model, now that we are confident that we're selecting the right parameters. So I'm not going to go over this again. These are the metrics that were introduced by Reza previously, the precision, recall, and F1 score. But now I can evaluate really how is the model doing on my flower prediction task. So you can see, so the test accuracy, it's 93%. So we're happy about it. And then you can see also we have different metrics for the different classes. So this corresponds like to class 0, class 1, class 2. These are the different types of iris in the data set that we have. And you see that the precision, recall, and F1 score, we all want them to be as close as possible to 1. So we are happy about this result. Now we have solved our task of being able to classify the different flowers in their own specific species. And then I told you that we're working on the decision tree. And a decision tree, one of the great things about this is that you can visualize your model. You can really see how it's working in practice. So this is my decision tree. And basically the decision tree is answering question at every node. So based on the features. So I told you the petal length is one of the features. So now if it's lower than some value, then I go left. If it's not, then I go right. And then I restart. So if the petal width is lower than this value, I go left. And then I go right. And this is how the model is going to be able to classify the different samples of the data in the right classes. So, and then this is in the appendix, but I just wanted to let you know that there is also a simple example that is helping you to understand more about how the different metrics work, how you can count the number of true positive, false positive, and it gives you an overview. So if you're interested about the different metrics and some of their limits, then it can be helpful to read about this, but I'm not going to cover it in this talk. So if there is no specific question about this notebook, I think I can hand it over to Reza again.
A few comments that I want to make based on the questions that we had in the chat. One is that about the validation and cross-validation and how to tune the parameters. So as Thomas mentioned, grid search is one of the ways that you tune your parameters. The goal is that your model has a few parameters, like in the decision tree, we have the depth as one parameter, we have the number of leaves, and we have more and more parameters depending on which model you are using. The goal of using that validation set is to find the best parameters and hope that when you test it on your validation set and say that this set of parameters are giving me the best results, the minimum number of mistakes, that can generalize well to unseen data set as well. So grid search is one of those, but yeah, as some people ask in the chat, that is correct that it can be very time consuming, especially when we have models that can have millions and millions of parameters. And in those scenarios, we won't use grid search. There are some other approaches based on Bayesian optimization or some smart methods that you don't need to try every single scenario anymore. And then based on those, you try a few, you learn which parts you have to explore more, and then based on that, you optimize your parameters. And you can check Optuna package. I wrote that in the chat for more intelligent hyperparameter tuning approaches. And the other thing that I suggest everybody to do is to just play around with the parameters at your own time and then change the max depth, reduce it, and then see how it affects your output, how it affects your classification results. And also try different models as well. Decision tree is one of them. You can try XGBoost, you can try random forest. Those are also models that are embedded in scikit-learn, and you can just import them in a similar way that Thomas presented for decision tree, and then let them train and then compare the performance with decision tree. Okay, nice. So now let's go back to the slides for a few minutes, and then we'll come back to another notebook as well. So we talked about classification problems, and Thomas presented two different examples for you as well. Now let's talk about regression. If you remember that we were discussing it, regression is also very similar to the classification, but the difference is that your output space Y is continuous. It's not anymore class 1, 2, 3, and 4. It's a continuous space that any value can be a solution for you. So one simple approach for that again is linear regression. So this Y is your output, and you have some feature vectors xi, and you assume that your input-output relation is linear. Then you can write it in the matrix format as X transpose multiplied by this beta plus some noise. And in the 2D example, we have some data points here, and the goal is to fit this line so that we minimize some error. Again, similar to the classification problem, the goal here is to minimize some loss function. Two famous loss functions for the regression problems are mean square error, where you are taking the difference between the predicted value and the actual value, and then take the square and average it over all your data points. And the other one is mean absolute error. So on the right, you see the loss functions. So if you're at 0, you don't make any mistake. It means that your target value is equal to your predicted value, so you don't want to penalize. And as you get far from 0, then you penalize more and more, depending on which loss function you are selecting. So one drawback of mean square error is that it can become sensitive to the noise because it penalizes a lot when you get far from this 0. So we can use either mean absolute error instead or Hoover loss. So the Hoover loss is another loss function that is approximating mean square error and the mean absolute error so that it can benefit from both of them, because the mean square error can give you better generalization around the boundary, around this area, but it's more sensitive to the noise when we get far. But the mean absolute error has better generalization when we are far from the boundary and give you more sparse representation of the data, but it's not doing as well as mean square error around the boundary. So there are also different loss functions that you can consider when trying regression models. And beyond linear regression, again, it's not, I don't think in any real world application, we have like linear and nice linear representation from your input to the output. So there are more complicated approaches like decision tree, XGBoost, and neural networks, which we'll talk later about, that can help you to learn this input-output mapping. Now let's go back to another notebook and try one regression example, and then we'll come back and discuss about neural networks.
Oh, yes. So I'm going to be very quick on that one because all of what I've explained to you on the classification problem for the flowers will be exactly the same in the regression settings. And we're also going to use a decision tree because this can handle both classification and regression settings. But I just wanted to provide you an example of regression too because it's an interesting application. So on these data sets that we have different features about houses, households, and we want to predict the price of the house. So it's called California housing data set, and it's pretty common. And so you can see here that I loaded exactly the same using an API. And then here are some samples of it. So you can see the median income of the household, the house age, the number of rooms, the number of bedrooms, and also the population in the neighborhood. And so using all of these features, we want to predict a target, which is now a continuous value that we want to predict. So again, it's going to be the same. We need a training, validation, testing set. And so the validation is used to get the best hyperparameters for the testing case in operations. We're processing the features, and you can see here that the training set, the validation set, and the testing set are much bigger than it used to be in the previous example. And in fact, this is an interesting observation that you made before, talking about how it was impractical to use grid search in real scenarios when we have lots of parameters that we want to try. And it's also the case here. And that's why you can see that I've reduced the number of values that I'm testing because we still want it to be fairly quick to run. But yes, as Reza mentioned, you could use Optina and more advanced methods to do that hyperparameter tuning. So I'm not going to go over this again. So we have different metrics that can be used in the regression settings. So some of them are the mean square error, the mean absolute error, and error squared that have different properties and different things that you can see. But one point that is really interesting and where I want to draw your attention is now we want to see the decision tree visualization. And you see that here, in that case, the max depth is 6. And just by looking at it, you can understand how impractical it is to take a look at the nodes one by one and understand in that case what is interesting, how is the model working, because it grow exponentially complex with the depth of the tree. And so I've just shown you like a smaller sample of them, and you can see that the splits are based on the median income here, which if it's lower than some values, we go to the left. Sorry, I didn't hear if it was a question or... Okay, so maybe it was just a mistake. So I just wanted to draw your attention that when the problem becomes a little bit more complex, it can be very impractical and we lose about this interpretability. But here, just taking a look at the first splits of the decision tree, you can see that the median income is a very important feature as this split is based on the median income, this split is based on the median income, and this one too, and this one too. So this is used by the model to capture the first idea of what would be the target value and trying to predict it correctly. And so that's it for this notebook. I think if there is not any specific question in the chat, we can just go to the next step. Reza.
Okay, so I try to answer some of the questions in the chat.
I can continue answering to it.
Okay. Okay. Now let's talk about neural networks, which are one of the most important machine learning models that you can see their applications everywhere nowadays. And we'll talk about some of the basic architectures and how these networks are being trained at high level. And then again, we'll go through some demos and play around with some parameters so that you get some intuition about neural networks and how the training works, how the parameters are working. So inspired by human brain, neural networks are machine learning models that try to learn input-output mapping through a combination of some linear and nonlinear transformation. So this is a schematic of one neural network where you have some input layers, you have some hidden layers in between, and then you have some output layers. So the elements of this neural network are some linear transformations or the weights on these edges that we see here, and some nonlinear functions. So at each layer, we multiply the inputs by some weight values and add them with some constant bias. And then we pass them through some nonlinear functions. And the goal of neural networks is to learn these WI and BIs so that we can again minimize the loss function. So again, if we zoom out, we are going to do a input-output mapping and learn a function approximation through some parametric model. And given some input data, we want to minimize the overall loss. We want to minimize the number of times that we make mistake if it's in a classification scenario. So some of the most famous activation functions that can be used are ReLU, which is this black dotted line dashed line that you see here, tangent hyperbolic or sigmoid activation function. So these are different nonlinearities that are common in neural networks that you can use to train your model in the architectures like fully connected that I'm showing here. So and propagation works in a simple. So for the input, every layer we multiply this value by some weights, and then we take the value, the resulting value, and once we have the output of these neurons, again we multiply by different weights. We pass it through again some nonlinearities, and then hand it over to the later layer, and we continue until we get to the final layer. And at the end, once we have the output, we can calculate the error or the loss between the predicted value and the target value. And the goal, as I mentioned before, is to find these variables, W's, and the biases that minimizes the overall error. And we do that by doing gradient descent. So you can consider this as a updating rule that you want to minimize your overall loss function if we consider this function as your loss, and you start from somewhere, you initialize your weights using some random number generator. You start with some random numbers, and wherever you are, you take the gradient, then you take one step in the direction of the negative of that gradient, and then you update the weights, you calculate everything. Again, you continue to the next step, and then calculate the gradient, and you continue until you get close to the optimal point where your gradient should be close to zero. And we have some parameter here, alpha, which we call that learning rate. It tells you that from one step to the other one, how far you want to take that step, how long that step you want to be. So if you increase the learning rate too much, then you might bounce here and here. And if your learning rate is very, very small, then it takes a lot of time so that you get to your optimal point. So how we do that, I don't want to go through the math here, but and just want to give you the overall idea. So we talked about the forward pass and discussed that to optimize it, we have to take the gradient of the output. But what we need to do is to use the chain rule in the derivatives, and pass the error, calculate the derivative of this error with respect to each one of these parameters and the input data, and then update those weights, and then pass it to the next layer and next layer and next layer. And we continue this over different epochs to minimize the loss. And Thomas talked with you about training and validation. So in the neural networks, we have one training loss versus number of epochs, and we have some validation loss. And as we discussed before, this validation loss is the validation data is a guideline for you to know how far you have to train your model, or when is a good time to stop. So based on this curve that we see, the area around this dashed line seems to be a good stopping point. Why? Because if we do not train up to this point, then we see that the loss is still decreasing. Both the training loss and the validation loss are decreasing. And also, if we pass this point and continue training, after a certain point, the validation loss is starting to increase. So it means that the model is not able to generalize anymore. You are making the model more complex, and actually your model is memorizing instead of learning the input-output relation. And that is not something that you want to do, because when this is happening, your model is not going to be able to predict well on the unseen data as well. So this is an example of a neural network for handwritten digit classification. So we can consider this as an image where each pixel here can be considered as the input of the node. So each one of those represents one of these pixels, and we flatten this matrix. We flatten this matrix and put it here. And then after the model is trained, the pixels will be multiplied by weights, go through the nonlinearities, again go through some linear transformations, nonlinearities, and then the neuron with highest probability will fire, and we know that which node, which class that data is coming from. So that's the feed-forward neural network. We have some other architectures of neural network that are designed for more complex tasks and are able to capture different structures and dependencies in the data. One of the most famous ones in convolutional neural network. And the idea is to design some convolution operator in two-dimensional space so that you can capture the relation between the neighboring points. So in this image classification task, we know that the pixels in an image that are close to each other have a high correlation. So we want to capture those correlations through using a convolutional operator, as you can see on the left, and then combine those information, pass them through some nonlinearities, again send them to the next layer, do the convolution, nonlinearity, again send them to the final layer, and then make the decision. And the optimization is almost the same. We also have other types of neural networks which are designed for time series analysis or sequence analysis, where you want to have temporal dependencies in your data, right? Recurrent neural networks. The idea here is to make sure that the decision that you make for the next data at time t is depending on the decision that you made at time t-1, and capture the time dependency in your data or temporal dependency in your data. This model has some limitations, like vanishing gradient, or exploding gradient, because if you continue this for a long sequence of time, your gradients will become more and more and multiply together, and you cannot train your model in a stable fashion. So there is another kinds of networks called LSTMs, or long short-term memory networks, that came to address those issues by having some forget gates, so that you do not remember everything when you get far from the point that you want to make the decision. That's kind of the overall idea that you have to understand from it. And then we have graph neural networks that are designed to operate on graph structured data, where the nodes can be entities and then the edges can be the relation between the data points. Now let's move to a TensorFlow playground and play with some parameters of the neural network. I will send the link to the chat so that you can also try it. Sorry. Okay. Can anybody now see the Google Chrome page that I have? Okay, so I assume that you can see it. So here we can define the problem. Let's say we start by this linear problem on the bottom left side, that we have two classes of data that are linearly separable. We can change the number of hidden layers by adding or removing, like by putting on the plus or minus. You can add or remove the number of layers. And at this layer, you can add or remove the number of neurons as well. So we start by something simple. And this is also a simple task. You have the data being linearly separable. And the activation function, we can select as linear. This learning rate is that alpha that I was talking about previously. And this regularization is an additional term that you can add to your model that can regularize the model so that it doesn't get overfitted to the data set. And we can play around with it and see how it will affect the result. And here I select classification because I want to focus first on the classification problem. So if we click run, then after a few epochs, we see that the model can separate the blue and orange areas from each other. Now let's say we go to another problem that is more complicated and use the same architecture for this one. Okay, so we see that the model cannot converge very well, and part of it is because we don't have any nonlinearity in the system. The activation functions are all considered as linear. So we change the activation function to either tangent hyperbolic or ReLU, and then again we hit run. Okay. And we see that the model is not able again to learn completely. So this can be because the architecture that we selected is not complex enough. So what we can do is to regenerate and then stop, maybe add more neurons here, then click run. And as you can see right now, the model can differentiate between the blue and the orange areas with a very perfect classification boundary and performance. Now let's see what happens if we add regularization. So we say, let's add L2 regularization. Basically, it penalizes the weights with L2 norm or a squared value of the weights and doesn't let the weights to become too large. And this regularization rate, again, tells you how much you want to regularize. We will increase this. So what we expect here is that if I increase this regularization term, it will bound the model more and it doesn't let it to have weights that are too complicated and it might not converge. And again, as we see here, the model is not converging very well and cannot learn. So we can close this one and then use maybe a smaller learning rate. And no, okay. Okay. So again, going back to what we were talking about, hyperparameter tuning, these things that we see here, the regularization learning rate or regularization rate are some hyperparameters that we need to learn. And as you can see, sometimes when you add it based on the problem at hand that you have, they might not be able to converge to what you want. The other thing that I wanted to talk about is if we just stick to sigmoid activation function. So if we have sigmoid, again, sometimes it becomes very difficult to converge. Not always, but sometimes. And that is usually because the sigmoid function has always positive gradients. The derivative is always positive. And in some tests that you have more complicated input-output relation, the gradients are not that informative, and then you cannot learn that input-output relation very well. Or it will take you a lot of time, and the model will need a lot of epochs to converge to that. So I will let that here. I will stop here and see if you have any questions in the chat, and then we can continue.
I think I answered to some of the questions in the chats. I think one question is how to decide the number of hidden layers that I see. So in the settings that I discussed right before about how to tune the hyperparameters, the number of hidden layers could be seen as the depth of the decision tree. And so you will do the same kind of thing. You could use like grid search or any other tools. This is all about hyperparameters tuning, and it will grow the complexity of the model.
Are we good?
I think there is also one other question that came twice is how can, and this is a good question, how can we understand that the model is memorizing and not learning?
So the error that one way is to look at your loss function. That is the first thing that you always have to do, is to look at your loss function and compare the validation loss and the training loss. The other approaches depend on the number of data points that you have. Sometimes you can do cross-validation, somebody asked in the chat before. So you can divide your training and validation set into different sets that are not overlapping and repeat that process again and again and report the average and the standard deviation of your error metrics. And if on some of them you are doing very well, on some of them you are not doing very well, it means that you are either underfitting or overfitting to your data. So you have to change your hyperparameters and make sure that you are doing, you're learning that mapping good enough. But you have to be careful. Some mistake that sometimes happen is that you do not touch your test set until you are done with your parameter tuning, your training, everything. The test set, you touch it only once when you want to do a final assessment of the model. Because sometimes if you do not see the test set during the tuning parameter or the test or the training parameter directly, what can happen is that you train the model, you validate it, and then you go check your test result and see, oh, it's not that good. So you go back again, you change it, you train, you validate, and you check the test data, you see it's not good and that much. Then you continue this loop. So it's kind of, you are doing the grid search manually by looking at your test set over and over again. And that can result in having overfitting or underfitting in some tasks, especially when you have limited data. So that's something that you have to be careful about it. Okay, now let's go back to the presentation if there is no more question. And again, please use that link and try different settings. And if you have questions, you can send in the chat or after the workshop is done. Okay, now let's talk about natural language processing. So this is a field of AI and machine learning that aims to teach machines to read, understand, and derive meaning from natural language. So we all might have worked with ChatGPT so far and see how impactful it can be on our everyday life, and how understanding human language can facilitate so many different tasks that we have. And over the past few years, this curve on the right shows you the y-axis is the number of operating points, the number of flops, like number of computations that you need to train those models, and then the x-axis shows you the year. And we see that we are extensively increasing the size of the models, and we are training more and more complex models every day to learn the human language and also understand it and be able to communicate with people. And still, we are not there yet. There are some limitations of these models, like hallucination or not being reliable in some tasks that needs extra work. So we want today to focus on some fundamentals of natural language processing and see how we can represent words in embedding a space and in vector spaces, and how to work with them for some simple classification and sentiment analysis test. So some applications of natural language processing are for name entity recognition. So the goal here is to identify different entities in a sentence or text, like what we have here. So in the sentence, Apple was founded by Steve Jobs in California in 1976. We see the words in different colors. And the goal of name entity recognition problem is to identify the entities and then see which class each one of them are from. So you can kind of consider this as a classification problem where your input is a text instead of just raw numbers or continuous values. The other task is sentiment analysis. So you want to determine the emotional tone or sentiment of a text and see whether it's positive, negative, neutral, or something else. So again, this can be considered as another classification task where your input instead of continuous variables or different features like images are text. So for example, in this text, the movie was absolutely fantastic. I love every minute of it. So the sentiment is positive, and the explanation of that can be based on having the words fantastic and love to be representative of expressing a strong positive emotion. The other task is machine translation, where you want to automatically translate text from one language to another, like from English to Arabic or English to French and vice versa. So the first step in language processing is pre-processing of the text. You have to clean a structure and prepare your data for the downstream NLP task that you have at hand. So for example, the first one is tokenization. If you have a sentence like I love NLP, the goal is to break it down into different tokens, I, love, and NLP. And then after that, you can normalize it and make sure that everything is lowercase and remove the punctuations as well. And then you want to do a stemming, which means that you want to reduce the words that to their base meaning, and then remove the stop words like there is, which does not necessarily carry significant information. So these are some pre-processings that you do when you want to perform NLP tasks or text processing. But the question is that why do we need word representation? So natural language is complex, and the context, grammar, and semantics make it more and more complex compared to the problems that we have at hand, where it's either just the numbers, regular numbers, or regular continuous values. And the words themselves might not have the whole meaning for the computer. And depending on where they are presented in the sentence, they can have different meanings as well. And the goal of representations are to bridge the gap between human language and machine processing, so that we can use machine learning and deep learning models to perform either name entity recognition, sentiment analysis, or machine translation tasks. So the few challenges are that the words can have different meanings. Like the word bank can have meaning from a financial institution perspective or riverbank. We have a lot of other words that can have different meanings. The other issue is that some words have similar meaning, but they have a slightly different context. They are synonym, but depending on when they are used, they can have different sentiment or different meanings. And also the meaning of the words usually depend on the surrounding words as well. So that is something that we have to consider when we are trying to represent the words and embed the words in a new vector space. So one simple idea of working with the text data is to do one-hot encoding. So what does that mean? It means that for every single word that you have in your dictionary, you represent it with a vector that it has all zeros except in one location. So you have zeros everywhere except in one. And then the same thing for the word dog. So everything is zero except in one location. And that's the unique representation of word dog, and the same for the cat. So this is challenging. The first challenge that you can imagine is that the length of this vector can increase significantly, and actually is same as the length of your vocabulary, all the words that you have in the vocabulary. And the dimensionality can rise significantly. So the other one is that all the words in the one-hot encoding criteria are equally distant. So the distance between cat and dog, and maybe if we have another word like bank or car, are always the same if you take the difference. So that's also not good. And there is no notion of similarity in one-hot encoding. So cat and dog are different, but they are both animals, and they are more similar to each other compared to car and motorcycles. So we need to use an approach that can give us that ability to have the similar words close to each other and dissimilar words far from those. The other challenge of one-hot encoding is that it's not capable of handling new words efficiently. So if we formed a dictionary and we have one new word added to the dictionary, then we have to revise all the encodings that we have done and generate new encodings based on that, which is not computationally tractable. So the goal is to have context-aware word representation, where we are going to encode the similarity in the vectors and make sure that the words that are similar to each other are closer to each other. And we do that by looking at the large corpus of text data and then identifying the words in different sentences and have a better representation that captures the context of the word and the meaning of the word. So that idea is coming from word vectors, which are also known as word embeddings, that can be considered as numerical representation of the words in a continuous vector space. So as we discussed earlier, the idea is simple. You want to have the words that are similar to be close to each other. For example, here we have king and queen, and we have the cat. So we want these two vector representations, the continuous representation. We don't have 0 and 1 anymore. The numbers are continuous. We want the distance between these two to be closer compared to the cat, which has a different meaning and different context. And we will see some nice examples after I'm done with the presentation in the notebooks, that we can have a presentation of the words in two-dimensional space and see how similar words are close to each other. So word2vec is one of the approaches that is famous for creating those vector representations or vector embeddings based on neural networks. So in this setting, as I discussed earlier, we have a set of sentences, and based on that, our goal is to map each one of the words into a new space, where the representation of similar words that appear in the same sentences or similar sentences be very similar to each other. So one of the approaches that implements word2vec is a skip graph. So each vocabulary represented by a vector, we go through each position in the sentence T and consider a center word as C and the context word as O. So the goal is to use similarity of the word vectors for C and O to calculate the probability of O given C. So I will give you an example in a few seconds to make it more clear. And our goal is to adjust these word representations and word vectors to maximize the probability given some training data. So on the right here, we see a high-level overview of this, that we want to use the word at the location T to predict the words that appear before that word and after that word. So we use that context word to predict the words that are outside and are close to that. So in this example, we have a sentence, part of a sentence, problems turning into banking crisis as. So we consider this word that is shown as red as the center word, and the goal is to predict the conditional probabilities of seeing banking as the next word given into being as the center word, and probability of the turning being the word before that given into being as the center word. So the goal is to learn these probabilities. And then we do the same process for banking, and then same for crisis, and so on. So the objective function here can be considered as this likelihood function, where the goal is to maximize the overall probability given some theta, which are considered as the parameters of that network. And then because we usually like to work with likelihoods instead of likelihoods, and also work with summations instead of multiplications. So we take the log of this one. When you take log, all these multiplications will turn into summation. And because we usually like to minimize instead of maximizing something in optimization, so we add a negative here as well. So minimizing this objective function is same as maximizing the predictive accuracy or predictive probability that you have. So again, the goal is to minimize this objective function. We use 2 vectors per word W, one when that word is positioned at the center, and one when it is the context word. And these 2 vectors, the vector representations, are considered in this theta variable. So we are going to learn those representations to minimize this objective function. And then we can model this probability as this function, where the top value, the denominator, is comparing the similarity between these 2 words, and the bottom part is just some normalization factor so that it gives it a meaning of probability. So technically what you are doing is that you are comparing the similarity between the word representations, and you want to come up with a word representation that the vectors for the similar words have closer distance to each other compared to the ones that are dissimilar to each other. So that was a skip-gram method. There is also another method called CBEL, or continuous bag of words, which is using a very, very similar approach, but with a slightly different idea. In the skip-gram, as we discussed, we look at the center word and predict the outside or context words. In the CBEL is the other way around. So you look at the words that are around it, and then you want to predict the word that is located at the center. And then this way you can learn, again, the word representation, which in the 2 different notebooks, we'll play around with them. And then Thomas will talk about one example to see how this word representation can help you to have some logical transformations, like summation or taking the difference of 2 different words. And also we'll go through some sentiment analysis problems as well. So I want to stop here and then hand it over again to Thomas. And I highly recommend that you also download the Jupyter notebooks that we have for the last part and start playing with the parameters as Thomas is explaining.
Yes, okay. So now, as Reza introduced to you, we're going to talk about word embeddings, and I'm going to show you some of the interesting properties of these embeddings and how it works and how we play around with this. So as Reza mentioned, the idea is we have some text data and we want to transform it into a vector, because machine learning models and deep learning models are able to learn from numbers and vector numbers. And so that's why we need to translate it into their language. So again, we import the different packages, and here we load some pre-trained word embeddings. So basically what is happening here is I load a mapping from the different words of a corpus into like a 100-dimensional vector. So you have 100 numbers of values, float values, for each specific word that you have in this database. So you can see that it can be pretty big, but also you can assume that there is thousands and if not millions of words. So it's interesting to have this dense representation in just 100-dimensional vectors. So this is how it works. It loads Again, I've pre-run it because it can take a few minutes to load these because you can assume that it's pretty big. The number of words in this mapping is pretty big. So then you don't have to worry too much about this data, but what happens is that I'm loading the embeddings and I want to visualize them to show you some interesting properties. So what we use here is PCA. So PCA, it's basically just an algorithm that is used to reduce the dimensionality to just 2D so that we can visualize, because you can see that we cannot visualize further on a simple notebook like this, and even in real life. So the intuition that I want to give you is that I've used like a list of words. Some of them are related to each other, some of them are not. And we want to see where are they in the embedding space. Are they close to each other? Are they further to each other? So you have king, queen, man, woman, etc. So, and this is the representation. Oh, maybe I can unzoom a little bit. Yes, so this is the representation. So here, it's very striking that there are like interesting properties. You can see clusters of words such as car, plane, and bus that are very, very close to each other. So about transportations, some of them about stories, movies, horror, movies, scary, story, book. These are also relatively close to each other. Then you have cat and dog that are very close, man and woman, mother, father, king, queen. So you can see that even in 2D, we can see that these words have vector representation that tends to put them very close to each other when they have similar meanings. When their semantic meanings is very close. So this is an interesting property, and this is also why we can use them for further tasks that exploit the meaning of the words, and this is how it's able to learn. There is just one thing that I want to clarify. So it's these embeddings that I'm showing to you right now. They have been pre-trained. So it means that I've just loaded the mapping, and they have been pre-trained on Wikipedia databases that contain lots of textual data. And so that's why it has been able to exploit the meaning and the contextual relationship between the different words. So then I want to give you some idea about what are the different things and that we can see. So we can calculate, for instance, the cosine similarity. So we want to do some similarity search, because now that we have vectors, we can identify and try to see how are they similar to each other. Are they pointing in the same direction? Are their norms closer to each other, etc. So we can compute the cosine similarity. So this is the dot product over the product of the two norms. So this is pretty simple, and this is contained between -1 and 1. So 1 indicates that the vectors are are identical. They're very close to each other because they have the same norm and they are pointing in the same direction. 0 means that they are orthogonal, so there is no similarity. So you can see it because they are very different from each other. And then -1, it suggests that they are going into opposing directions. So it's maybe one word and it's contrary. So I wanted to show you like a very simple example. So you have the word car, and you want to take a look at what are the similar words to car. And what you can see here is that the ones that have the higher score are vehicle, truck, cars, driver, driving. So all of them are very related to car, and we can get that from the semantic meaning. They are very close to each other. But also in this representation, you assume that it would be too easy if it was perfect, and if the meaning was very easy to get and we could learn everything like this. So there are a few biases, few problems that we have. So one of them is the polysemous words, which are the words that have multiple meanings. So one of them can be leaves. So I'm showing you the example, and then when you'll be playing with the notebooks, you can also explore other examples and see where it works, where it doesn't work. But leaves, it can be the word, the verb that means I live, I'm living, but also the leaf. So in botany, so related to trees, etc. And you can see that here the most similar words are text, ends, stems. So some of them are related to the verb, and then some of them are related to flowers, leaf, grows, trees. So so you can see that it captures two different meanings. So it says that, for instance, some of them are similar to each other, but it's not really the case depending on the context. Then there are other relationships. When we have vectors, what can we do? We can subtract them, we can sum them, we can play with them. And so we can do arithmetic operations on these vectors. And so here, this is what you can see. This relation, so it's king minus man plus woman. So basically what we're trying to get from that is X is to woman, what king is to man. So you can see that there is a vector translation, and we want to see if it's captured. So I showed you two examples. So one with king, man, and woman. So we recall X is to woman when what king is to man. So we know from our knowledge that it should be queen, and queen is indeed the most similar word and the one that is the first one to be outputted here. So it's interesting. And then we can go to another example. So X is to woman what grandfather is to man, and X is grandmother. So again, it's very interesting to see that these relationships and these translations are captured by the simple vector representations of the words. And then I showed you another example, which is based on countries and capitals. So the idea is to have X is to Syria, what Cairo is to Egypt. And you can see that you have this representation and the vectors are very close to each other. And it gets that the capital of Syria is Damascus here. So it can have very interesting properties and very advanced ones, such as like this. It can identify the capital of a country based on another example. So it's really able to understand this concept. Then Reza, let me know if there is any specific question that I should answer. Otherwise, I'll go to a more real world example in which we can use these embeddings.
No, I think it's clear, but a few comments that I can make is that here we are showing the two-dimensional representations. So this can have some, we will lose some information when you go to 2D. So the original vector representation are in high-dimensional spaces. And here PCA, which is standing for principal component analysis, is used to map that high-dimensional data into two-dimensional space. So even if the word embeddings are perfect and are actually mapping the data points and make sure that all the similar points are close to each other, that mapping from high-dimensional space to 2D space can result in loss of some information. So that can be the reason that somebody asked a question that why some words might not make sense, are not close to each other as you're supposed to. On top of the limitation of the data set that those word embeddings are trained on. And the other question was about embedding sentences, which I'm trying to answer, but I think we'll see examples in the one that you're going to talk about.
Sure. Okay, perfect. So we're going to go to another example, I would say more real world example. So how can we use these word embeddings in practical use cases, especially for classification, because we talked about classification. So how can it be helpful? So one of the data that we're using here is, it's called IMDb. So it's Internet Movie Database. So it's basically containing lots of, a collection of movie reviews that are labeled with their sentiment score that can be either the sentiment is positive, negative, or neutral. And so what we want to do is we have these text sentences and we want to do classification. So we're just coming back to the same problem. So how can we express these sentences into embeddings? How can we extract the features that we want to put them into further machine learning tasks as we've done previously? So before going into details, I wanted to clarify two things. So in the previous notebook, I was showing you pre-trained embeddings. So there are mostly like Tuve, Glove, Bird that you can download from the web, and they have been trained on huge corpuses of data, such as Wikipedia or whatever source of data it can be. And then so they are able to capture some general knowledge about the words and their use and etc. But there are also some other embeddings that we can use, which are embeddings that we can train ourselves. And the idea is we want to create that representation, that numerical representation and vector representation of the sentences and words based on a downstream task. So we want to determine these representations just by learning and doing forward propagation and back propagation through different steps, and hopefully having the best embeddings at the end, but just for our task. So it might not generalize well, but it's built for our classification problem in that case with the sentiment analysis. So again, it will be the same architecture as before. So loading the data set. And then we create the model. So here we have a deep learning model, so which is the first time, and so it's a neural network. And Reza, I've told you about this. So we are trying to build our model, and you can see that here. So we have our embeddings, which is basically an empty matrix at the beginning, and we're trying to map everything into like a 108 vector space. Then you use an LSTM. You can see how great it is to use these tools, because these are open source tools where it's very easy to create a model. You just have to add LSTM and not recall about all the details of the architecture, etc. So we build our models. I'm not going to go into too much details, but this is the idea. And you see every layer. So here we have the embedding layer that we've created ourselves. And you can see that it's a huge number of parameters, more than 1 million of them that needs to be learned through the learning process, because the output dimension of the vector will be 128. Then we have our LSTM. Then we have a simple dense layer, dropout layer, dense again. These are very common layers. I'm not going to explain them, but they are used in lots of ways. And so we see that at the end, it comes to a number of total parameters that is 1,300,000. So it's a huge number of parameters that need to be learned. All of them have to be learned during the learning process. So it's going to take a while. And also that's why in this notebook, there is no hyperparameter tuning, because already the training itself can take a few minutes. I think it takes 5 minutes. So everything is run on my end, so I can show you. So you see, this is almost the same syntax as before. We do model.fit, and we train on the training data. We allow to have 5 epochs, and the training is going. And you can see that the loss is decreasing through the different steps. So it goes from 0.68 to, at the end of the last epoch, 0.17. So, and we have the validation loss and validation accuracy. So this one is the training accuracy and loss, and then you have the validation accuracy and loss. So now the idea is that we want to evaluate on our testing sets, and we get an accuracy of 86. But as we told you, there is something that's important, which is to monitor the loss, to take a look at them, and to also take a look at the accuracy. And what's important here is that, especially with the loss, I hope that you recall something from the earlier presentation of Reza about this, especially about overfitting. So here you have the training loss in blue and the validation loss in orange. And you see that after some number of epochs, especially like, let's say 2 or 3, the validation loss goes up again. So it means that we are overfitting, and we don't want that. So in practical use case, we would stop the number of epochs for the training to, let's say, 2 or 3, because the training loss will always go down as the model will start memorizing about all of the input data. But at some point, we want to be able to generalize on new data, which is what represents the validation loss. So, and you can see that the same appears on the accuracy plot. So after 2 epochs, the accuracy starts going down on the validation data set that corresponds to the new data that we receive. So yeah, so I think it's mostly it. So if you have any question about this example of classification using textual input data, I will be pleased to answer this.
Thank you, Thomas. A few other comments that I wanted to make. If Thomas, can you go please to the part that we do model fit? Yes, thank you. So you see again here, we have some hyperparameters. One of them is the number of epochs, which means that how much we want to train the network. And the other one is batch size. So that batch size means that how many data we want to load at each iteration to calculate the gradients. So when we have huge number of data points, we cannot calculate the gradient on all those data points at the same time because of the computational, the limitation in the computational resources. And even you have high-end GPUs for tasks that involve image data or text data with large data sets, you won't be able to load all the data and calculate the gradient. So this is related to a method called a stochastic gradient descent that you use to load the data sequentially, one after the other, and then calculate the gradient on those data points, and then minimize your loss. Then load the second batch of data, and then continue. And the other thing that I wanted to add was also in the loss function curves that we have. As Thomas mentioned, we are seeing that overfitting. So a few ways to stop the model from overfitting is to add regularization terms like dropout layer that was added in the architecture, or adding norm regularization for the weights. These are a few ways. And the other approach to stop the model from overfitting is using callback functions. I will also again send it in the chat, which actually is monitoring the loss function, the training and validation loss. And if during some epochs, we see that the validation loss is going to increase and getting far from the training loss, then we ask the model to stop and return the weights that were giving the model the best validation loss so far. And this way we save some computational resource, and also it doesn't let the model to overfit. I highly suggest you to start working on the notebooks and see how changing the parameters will affect the model performance. But a few things that I also wanted to add is that the data set that you use to train your models has a huge impact on how well your model will be able to generalize. Let's say in the task that you have image classification, and you want to develop a model that is making decision based on looking at the images, either for face recognition or for healthcare purposes for lung disease classification. If your data is not representative enough, it can have different biases against different populations. And also some other biases can be coming from the device perspective. So you train some model on a specific hospital, but it doesn't work on the other one because the distribution of the data will change. So making sure that your data is representative is one important factor. And the other one is the metrics that you use to evaluate your model. So today we talked about different metrics like mean square or mean absolute error for regression, and accuracy, precision, recall, etc. for classification. But in some scenarios, those are not the metrics that can evaluate the model perfectly. Like accuracy, in particular, is not a good metric when you have imbalanced data. Let's say you have 100 instances and 99 of them are from one class and only one of them is from the other class. So 99 healthy patients and only one unhealthy patient. So if you have a model that says everybody is healthy, you will have 99% accuracy. And you are missing the most important decision that you have to make. So there is always a trade-off And also you have to be careful that what is the distribution of the data? What is important for you? And what is the effect of the decisions that you can make? And what are the costs of the decisions that you make on one class compared to the other one, so that you can design metrics that are providing you more fair and more equitable perspective of how well your model is performing. Okay. So if there is any question, please either unmute or write in the chat. Otherwise,
Hi, everyone. Do you guys have any more questions? If yes, then you can put the question in the chat option. I think we are having some more questions. Dr. Reza, Thomas, would you like to address those, or in the next 5 minutes, preferably, and then we can wrap it up?
yeah, sure. So one question is, where can we find the recorded version?
Yes, it'll be available both on YouTube and Google Classroom.
One question is about overfitting. So that can result in low accuracy on your test set, same as underfitting. So underfitting means that your model, the model that you created, was very simple compared to the task that you had. Overfitting means that you memorize everything and your model was more complicated than what it has to be. So when it goes to the test phase, it cannot generalize well. So adding data is one approach, but it's not the only one that can help you. If you do not add regularization terms, as we discussed, again, your model will overfit. And Thomas, please feel free to answer questions if you see any.
I think we have one last question, and then maybe we can wrap it up.
Yeah, references, we will also add references with the slides and add so that you can either read or watch more videos.
Yes, also I will try to address two quick questions. I think there is one question on which model to use, and is there any better model in general, especially like for punctuation prediction? I think Yeah, it's important to capture this idea of using the right model for the right tasks, especially now that we have very large language models. And one idea would be like to fine tune these models. So even if they are very big, they can be specialized to some downstream tasks. It can be a pretty challenging task to do so, but I would say that this is the way to go. I think now this is going to be more the era of small language models that are especially working on specific problems and addressing the right answers on these short problems. Then I saw another question about the transformation in 2 dimensions for the embeddings. And the person was saying maybe it may lose some important features. And definitely, yes, it's the case. So just to clarify, the projection in just 2 dimensions was made just for visualization purposes. And in your downstream task, you will use the full vector, so 100 dimensions, and not the reduced one. So in the full version, you will not lose any information, but it's just on the visualizations of the different words and the relationships that you might lose something by reducing the dimensionality.
Yeah, and also just to add to what Thomas mentioned about large language models, Dean will definitely talk about it more in the next workshop for you. But one other challenge is that maintaining those models is expensive, and fine-tuning them over time is very expensive. And in some tasks, you do not want to share the data as well. So if you cannot maintain it, you have to share the data, especially in medical tasks or in some sensitive tasks. You do not want to send or receive data, and you have to maintain everything locally. So that is also another consideration, that when you are working on some models, it's good to have models that are good enough, but also you can maintain them locally or in a safe place, that you have control over the data that you are working with.
Okay, I think we have come to an end, and thank you so much for thoroughly being so attentive during the wonderful workshop session. Thank you to Thomas and Dr. Reza once again for giving us your time. And before going off, I would like request everyone to just come on camera so that we can, take a photo of all of us. And Amreen, if you're ready, can you just take the photos? And requesting everyone to come on camera.
Could I get like 1 second before we take the photo?
Yes.
Thank you so much. Thank you, Dr. Reza, and thank you, Thomas, for this amazing session. And if I'm not mistaken, please do correct me if I'm mistaken. This particular workshop is directly correlated with the datathon that the people are going to participate in. And it's going to be very helpful to go over this workshop thoroughly, the recordings and Google Classroom, all the notes, all the other references that you shared, to do well in the datathon, which we really encourage all of you to participate in. Not just to win, but to learn how this works and hands-on. And our datathon is built. This problem set that we're going to be working on is built in-house by us, by the Herwill team, with advice from Dr. Reza and Thomas and other experts. So please do participate. It's going to literally change your career path. So that's one thing I wanted to mention. Second was, a lot of questions are coming about the videos and where and when you're gonna get them. Typically, we try to upload our videos within 24 hours. It gets late, sometimes a little bit late, but typically within 24 hours on YouTube and in Google Classroom. So YouTube will be available to everyone who registered. That is about 830 people who registered for these classes. will be available to all until until the end of the workshops. And after that, it's only going to be available to the participants, that's you guys, in the Google Classroom. So that is another thing. So in the email, we do majority of our correspondence through the emails. So if you read the emails carefully, and if you don't find them in your inbox, do it. Do check your spam and junk folder and other places, or just message us. In the email, we try to be very thorough. So we give you the location of the videos and exactly the timing and other etiquettes, and who's going to do what and all these other information. So you will get another email from us before the next workshop, which is next Friday. Meanwhile, what we're going to do is send you another email by tomorrow, around the same time, to give you the location of the videos. Does that sound good? Okay. So either way, you can follow us on all of our social media platforms, so you can see all the updates there with your pictures and everything. Thank you so much again, everybody who participated, and to our experts.
Thank you, Farhana. Thank you, Herbal team. And thank you, everybody, for attending the workshop.
And please take a picture.
Thank you, everyone. Thank you
Don't
so
leave
much,
before
Farhana.
taking a picture. Thank you.
So if we can all look at the camera and smile the biggest, then Amrin will take the photos. Amrin, just let us know when you're done. I really hope that we're done taking the photo. My cheeks are hurting.
Yeah, it's done. It's done. Let's move on.
Okay. So for everybody's reference, our next workshop is going to be held on the 18th of October. That's a Friday. And the next workshop is going to be on understanding large language models. And it is going to be happening at 11 a.m. Eastern time, which is 9 p.m. Bangladesh time. And if I'm not wrong, that is 6 p.m. Egypt and Syria time, right? Yes. So I hope that all are clear with the timings now and the dates. Regarding the recording session of the two workshops, regarding the Google Classroom joining information, regarding the Zoom information for the workshops, everything will be communicated to you all via email. If you are not continuously getting any email from us, then probably then try to reach out to us with a different email address so that we can incorporate that email address on our database, because what is happening is that we are facing a lot of emails being bounced and being rejected. So it is very difficult for us to really identify the authenticity of the email addresses that you have provided. But rest assured, all of the important information will be notified to you within the next 2 days. And having said that, thank you once again, Dr. Reza and Thomas. And I will be closing the session now. And I hope that this was a wonderful learning session for all of you. And as Farhana said, these are preparatory workshop sessions for you to participate in our datathon. And we really want you to participate in our datathon. Yes, so all the best for the rest of the workshops. And we would hope to see all of you in the next one.